notice this is usually made out of platinum, very expensive mirror. You have to shape this mirror in a very precise way, and the mirror usually is of the order of 20 centimeter long because the beam is quite wide, and you capture this light, and then you go to your sample this way. So the source comes in here, you get focused, and then you go to your crystal monochromator. Okay, and if you can, so if you can't do these synchrotron, and I'll talk briefly about this shortly. You can also do with one fixed wavelength. You can just fix a wavelength like a lab source, laboratory-based source. You can just measure the angular distribution. Right? You can just tune the angular distribution. You get something called flower pattern. This is due to a group used to based in University Hawaii by the name of Chuck Fabi. He started his work, and now he's at UC Davis working, not working on these anymore. It's been quite a while since we work on this. And you got these flower patterns, and again, the approach is the same. Instead of calculating energy curve, how the diffraction pattern, the chi curve, like this thing, you can calculate the angular distribution just the same way by assuming a geometry of your surface, and then you can use some theory and then calculate and compare this angular distribution at a fixed photon energy, therefore fixed wavelength. Okay, so just briefly comparing the technique we have seen so far, we have looked at diffraction, we have looked at fine structure two ways, both the angle integrated way and the photo emission fine structure way. And just a quick comparison is that the LEAP, just to be aware, the LEAP is dealing with diffraction phenomena, so you are talking about a coherent length, right? Whereas in the fine structure technique, you're looking at a local structure. In other words, you have the photon comes in, create a photoelectron, and this photoelectron will scatter around. So in the case of XSEP, the interference of the incoming light interfering with the photoelectron wave give you the fine structure phenomena. In the case of RPES, or photoelectron diffraction, you are just looking at the photoemission signal. So the photoemission signal scatter off the atom, and interference happen, and then this photoelectron will come out, and you're picking out, measuring out the photoelectron signal as a function of angle in the case of photoelectron diffractions. Okay, so this is an attempt to try to show you photon comes in, and then your photoelectron will scatter off nearest neighbor, and then it go this way. In the case of XSEP, photon comes in, the photoelectron will backscatter into the emitter, affecting this absorption, and the light continue to go out, and that creates fine structure. Okay, so that's a bit of a difference between the photoemission fine structure and the XSEP. So as I said before, we require synchrotron. A synchrotron is a high energy facility. So here's the Canadian light source, so-called Canadian light source, based in the University of Saskatchewan. So the Saskatchewan government actually put a lot of money into this, and Canadian government, of course, put in close to, I would say, close to $300 million during the initial phase. And then Saskatchewan government continued to fund this. Sax Hydro actually give the light source a discount on the power rate, because you can imagine high energy physics facilities use a lot of electricity, so they actually get a discount rate as part of the Saskatchewan government contribution to this project. So there is a national project, so that means that all the university in Canada can request for beam time on this facility. It's a nice facility. It's quite nice in time, but if you live by, it's not so bad. There are a lot of, I think there are quite a number of beamlines now, close to over 10, between 10 and 20 beamlines at the moment, working beamlines on there, doing a variety of different experiments, from protein crystallography to infrared spectroscopy to XF. Certainly XF is there, one of the basic tool set on anything. This is a so-called 3GeV ring, 3 million electron volt, 3GeV ring, I think it's 3,000 million electron volts ring, very high energy electron ring, very tunable to UV photon type. It's a what they call a third generation synchrotron, which is a improvement, if you like, of the advanced light source, which started some years ago, about 20 years ago, I would say, at the advanced light source at Berkeley, at UC Berkeley, the home of Lawrence, who the inventor of the cyclotron, of course, right? The inventor of the cyclotron is at the so-called Lawrence, initially Lawrence worked at the so-called Lawrence Radiation Lab up in the mountains of UC Berkeley, and 6 Nobel Prize actually was, the whole lab has about 9 Nobel Prize winners created due to this national facility. There are 10 facilities there are 10 national labs in the States, and this is one of the national labs to produce possibly the most Nobel Prize in science since the Lawrence day, because all the element, right? Remember Seaborn is a Nobel Prize winner, and all the high energy physics facility initially was done at the cyclotron because they have the cyclotron. And if you look at the original cyclotron, they are not that big. The original cyclotron is about this. It's about 1 foot. You can go to Lawrence Science and take a look. And the original cyclotron is actually quite small. It's about 1 foot in diameter, and then Lawrence basically expanded this to build a building. So this the advanced light source actually is in the 184 foot cyclotron site. They just revamped the site and we built on that site on the cyclotron. The reason to do that was because it saved a lot of concrete, because the original cyclotron has about 2 meter thick concrete as the foundation for light source. So it's quite an amazing thing, because if you look at the Berkeley Hill, it's a very steep, it's a crazy place to build a national lab, because it's a very expensive place because you have to flatten all these little terraces to build your laboratory. But it is a gorgeous place to work, because when you walk down the hill, you can see the sun set and sun rises as you go down. But then you don't have time to enjoy the sunset when you're working there. So this is the original time. Sorry, this is the original when they started building the advanced light source, when they're working. Now it's full of activity. I think the light source have been operating for 20 years, and people are moving on, and they are starting to work on the 4th generation source. And this is, they don't build storage ring anymore. They are going to build something called a free electron laser. And in fact, Stanford has started to see light with their free electron lasers. Okay, so there are other facilities I just want to point out. So it's now become a standard tool. There are numerous facilities in the world, not just at Berkeley and in Canada. There are in fact many others, including the Japanese, the European, Electra synchrotron light, for example, in Trieste, Italy is a beautiful lighthouse, beautiful place to work. In Beijing, also in Taiwan, several places. There